continue to discuss. Let's move forward. And you think about that. Okay, so what is quantum computing again? I want to just remind you, it is nothing but you prepare a state, and then what happened? You perform some unitary rotation in the hyperspace of the vector. Then you perform another one, and you keep doing so. Eventually, you do some measurement. That is quantum computing. That's it, yeah?
You use unitary operator and unitary rotation as the same thing, different.
Oh, okay. Unitary operator. But because in quantum computing, it is just rotation, right?
Is there any other rotation?
It's only rotation in the hyperspace, right? Because you cannot stretch it. Otherwise, you change the length of the state. It's all rotation. Okay? Now, of course, we know that all these unitary operator must be reversible, right? So if you want, you can go back. They have their inverse. The only thing is that after you do the measurement, you cannot go back because it collapses to the basis, right? Because all the unitary matrix obeys U. Do you remember what it is? U dagger equals to? U inverse, right? So its inverse is always exists. Okay? I just want to remind you why this reversible is so different from classical computer. In a classical one, for example, you have a LAN gate. Your input is zero, AND gate. If input is 0, output is 0, right? You have input is 0, 1. What is the output? Also 0, right? So it's not reversible, right? If give you the output, you don't know what the input is. But in quantum computer, it has to be reversible. I showed you earlier already, right? So and we need unitary because we will preserve what? Do you remember? What is preserved when you use the say again? Yeah, orthogonality, which also becomes the inner product of any state, any vector preserved, right? So I think they are equivalent. Okay. Now, besides that, just take a look at here, maybe a little bit dense, but let's do it. Maybe this will prepare us later for the qubit, the broad sphere. But let's just now, eventually, we do quantum mechanics, right? After the whole class, so many days, we still have not done any quantum mechanics. This may be one of the intense ones. You trust me. See if you can understand this equation. Anyone want to explain to me what this equation means? It is the Schrodinger equation, but what does it mean from what you have learned so far? What is psi? A vector, a state, a vector, right? Then what will H be? He said it's a number, possible, but we're talking about the evolution of the states, so what would that be? Yeah, so this is just an operator. Although we call it Hamiltonian, which is related to the energy, but it's just an operator, okay? So this is vector. So what is matrix times vector? Vector again. So on the left, it shows you the rate of change of the vector. Okay? You don't need to memorize this equation, but I hope you appreciate that. As I said, quantum computing is not just the evolution of the state, right? How it changes, how the state rotates. So under different systems, like external magnetic field, you have a corresponding Hamiltonian, which is related to sigma c. You are going to rotate it. And how it rotates? The rate of change of this state vector is equal to this matrix times this vector. Okay, question?
So I guess here, put the value of that reduced time. That comes about.
That is not dimension. Oh, say again. You mean how you have this equation? No, this is just the rate of change the vector. It's just like the F equal to ma. You don't need the time. Just like F equal to ma. Think about this. Force equals to mass times dx squared dt square, right? The time is just this is just an operation saying the rate of change. How fast do I accelerate proportional to the force? How fast this vector rotate? Because this vector is a column vector, you have the coefficient, right? How this number change as a function of time depends on this, like a force. They are all there, yeah. The operator tell us how fast it change, yeah. First term, this is I, h bar just a constant. Planck constant, yeah. So ignore this. This is a so-called Planck constant. Okay. Huh? Reduced Planck constant. Sorry. Planck constant is h. Okay, and reduced Planck constant is h divided by 2 pi. Okay, you can Google. We don't use it now. Later, when we talk about the qubit, silicon qubit, we will start using it, and the broad sphere, how it related to the external magnetic field. Okay, now, but why I want to do this is not asking you to memorize it. I just want you appreciate the state rotate as a function of time is related to this h, the Hamiltonian, right? So why I'm doing? I just want to keep showing you. You don't need to understand fully now. The solution, what is the solution? This is a differential equation. If, let's assume that h is diagonal. Do you remember when the h is going to be diagonal? When an operator is diagonal, we mentioned a few times. Not transformation. I mean, you can represent any operator in any basis, right? Under what situation it is diagonal? Under what basis? In which basis it is diagonal? Under the eigenvector basis. It will represent it in the eigenvector basis of the matrix, right? So basically, if I represent H in the eigenvector basis of H, which is the energy basis, then it is diagonal, right? But don't worry about this. Just that if it's diagonal, then we treat it as a number. Then you will find that the solution is, I just want you to know the solution. That's it. Don't worry how to get the solution. We will cover this at the end of the semester. Right? At that time, we will really look into the Hamiltonian of the under external electric field for a spin qubit. But I want you to understand, to be able to tell me what is the meaning of this equation again. It says that the state of psi at t is equal to the state at t equals 0, the initial state, multiplied by this constant, this coefficient. Okay? You may get confused. This H isn't a matrix, right? I can exponentiate a matrix. We'll do that later also. Just swallow it, that it works. So this is a vector, this is a vector, and then this is a matrix. I can exponentiate a matrix, particularly when it is diagonal. It is very easy. Yeah. This one, you just do substitution. Then you find that it's satisfied. Try to substitute to d psi t dt. Then you're going to take negative I h divided by h bar to the front. Then you find that they match. Okay, I just give you. I did not it's not because I can see it. Many people can see it right away, but not because it is so easy to see. I just give you the solution. So don't worry about this. If you want to prove, just substitute, you find that it works. It's easy when it is diagonal. Just treat it as a normal number. Okay? Now, but here is what I want to say. Look at this. What is this? This is the operator, U. That is the so-called operator. Right? I start with a state. I have a vector in this quantum computing. I start with a vector, psi at t equals 0. I apply a Hamiltonian to it. It will evolve to another vector. Can be NOT gates, control NOT gates, whatever. It evolves. And this one is the U, the unitary operator. Okay, so basically, this equation is doing this. It's like saying that I have an operator, I have psi at t equal to 0. And after this gate, it becomes psi of t. But I roll it from right to left instead of left to right. Is that okay? Now, this is not, there's a lot of things, right? We'll discuss later. But the only thing, the reason I want to show you now, just want to remind you that what is quantum computing. I've been saying that it's just a rotation of vector in the hyperspace. Now I try to relate to you to the physics. And you trust me, this is the Schrodinger equation. Just like F equal to ma, you never criticize your teacher why F equal to ma, right? But you do have the feeling, if someone push you harder, you accelerate more. You have the experience. But man, we don't have experience in quantum mechanics. We are macroscopic object, right? So no way, you need to trust it. It's just like F equal to ma. You cannot prove F equal to ma. You accept it just because you have it. If I were lump, I don't have feeling, or I always just sit at one place, never have acceleration, I cannot understand F equal to ma neither. I also need to trust it. But I can be a genius. I can still can get Nobel Prize, right? Because I really don't need to prove F equal to ma. Just like Schrodinger equation is given. You cannot prove it. Okay, so you trust me this, and then I just want to tell you that this H is the physical system. Later we'll learn a little bit more. And from here you will see that what is the real meaning of a gate. The gate is this e to the power I h bar times t. Okay, and that's it, right? And now I want to further practice some math and show you that this is indeed unitary. Okay, so first of all, what is e to the power negative I h bar divided by I h divided by h bar t dagger? What is that? Anyone? Yeah, you will transpose and conjugate, but because this is a diagonal, I mean, we have not done the matrix yet, but what I'm trying to say is in front of I, what do? Becomes minus I, right? So it becomes I. And then I'm going to just give this dagger to H. Okay? But however, H dagger equal to H, this is given because energy is an observable, right? As I say, this is Hamiltonian is related to energy because energy is observable. So if it's observable, its corresponding operator must be what? When you are observable, what is the property of the operator? Remember? It's Hermitian. Okay? H is Hermitian. Right? Because it's Hermitian, that's why H dagger equal to H, right? So this one because of this equals to E I H divided by H bar T. Right, so I prove that this equal to this. Then of course, U dagger times U equals to E negative I H bar over H bar T dagger, because this is U, right? Times E to the power negative I H over H bar T, right? I substitute U is E to the power negative I H over H bar T, and then the whole thing dagger, right? But I just show you what is dagger. It is just E to the power I H divided H bar T, right? I just show you what it is. What is this? E to 0, what is this? 1, which is, but this is a matrix, so it's an identity matrix. So this is what? U dagger times U equal to 1, it is unitary. Yeah.
So what's the proper definition of a form? What do you, in words, if you had to describe Hamiltonian?
You can say it as just the energy of the whole system, kinetic energy plus the potential energy.
So let's say if I have a pendulum,
Mm-hmm.
Hamiltonian of that system is mgh plus half mv squared, because it's got
Yes. But this is just the value, but then you want to convert into an operator, there's some method to convert them. So that is, you need to work it in physics. So x is still x, but p, momentum, becomes d something dx. Okay? Yeah, so this one is like you need to go into quantum mechanics, right? But here we don't do that. We just take it for granted. And we only look at the matrix form. Yeah. But you're right, Hamiltonian is just the energy. But once we convert it to operator, it's more than that, because you can transform into different bases. Right? If you just work purely in the energy basis, the eigenenergy basis, then all the value you're going to get are just the energy diagonal, the eigenenergy. Okay. Now, I know this is a little bit messy, so let me say again why I have this slide. First, I want you to appreciate how a how a gate is related to the energy of the whole system. All of that you see now, right? It is because we have this H in the Schroedinger equation, and this is the operator. You rotate the vector. That is first thing. Second thing, further we realize that because in any physical system, it must have this operator. Then I prove to you it is unitary. That's why in all quantum computing gates, it must be unitary. Yes, it preserves the inner product, but that is a consequence of it. It's just because we have this operator in this form. That's why it's unitary. And then it preserves the inner product also. And then all the bases will still be orthonormal when you rotate them. And the last thing is a review of what is Hermitian, what is unitary, some math skill, right? And how to find the solution, no worry, right? Won't be in the midterm, but maybe in the final, because at that time we'll have studied the qubit evolution, spin qubit evolution under magnetic field. Yeah.
This might be a little bit of extrapolation, but if I can write, based on this slide, a spin vector in terms of time domain, can I not also write it in terms of frequency domain? Or is it not of any use in quantum computing?
Well, you can always write something in the frequency domain by doing the Fourier transformation. Yeah, but then your frequency component is going to be also have this dt, right? Your frequency component can change as a function of t. Yeah. Make sense?
I think, but
Yeah.
they're kind of thinking or methodology on
It does. Actually, if you decompose into the eigen energy basis, the eigen energy is like the frequency. Or h bar omega is equal to the energy, right? So then you can do different type of calculation to do simplification, and even do quantum Fourier transform or something. Yeah, there is something, but at this moment I cannot say whether it's useful. But it's useful, of course. We can do that, but not in this class. We don't see the use. Yeah. So